everyone. In this video, in this conversation with Vitaly. Hello, Vitaly.
Hello, Katya.
In this conversation, our goal is to explain the fundamental concepts of neural network theory. We are going to hope to provide very basic high-level grounding necessary for very basic understanding, so that further we can have more in-depth investigation of specific topics, ideas, and implications across various fields. So let's start, and let's start with the very basics. What is scientific theory?
Good question. So I think that broadly speaking, scientific theory is a mathematical framework, a framework that can be used for modeling phenomena. And of course, the richer the framework, the more phenomena you can model and better model. The more experiments or observation it can explain, the better the theory. For example, you should be able to take a system, perform some kind of measurement on the system, then go to your theory, carry out some calculations, and predict what the state of the system will be at some later time. Now, if the predictions agrees with the experiment, then your theory is good. Now, of course, right now we're working in a situation when we have a lot of observations, a lot of experiments, and before we actually can propose a given theory, we should first try to see what those experiments and observations are. We should also try to learn the existing frameworks and the theories. And so this is a somewhat challenging task, but perhaps anyone can do that with enough foundation, with a strong enough mathematical framework with which you start.
And what is the theory of everything?
Well, the theory of everything is, as the name suggests, should be a theory that is capable of modeling everything. The mathematical framework which is rich enough to model all known phenomena. And that can include not only natural phenomena like physics or biology, but also economics, politics, or even art or philosophy. So everything should be modeled. Now, of course, that would be a real challenge. And usually when people say they have a theory of everything, what they really mean is that they have a general enough framework that is general enough to model some large class of phenomena. And strictly speaking, it is, of course, incorrect. But as long as you're explicit about what you are modeling, what you are not modeling, then there is no problem. After all, the theory of everything is just a buzzword that people use.
Do these theories tell us the literal truth of what reality is, what is literally going on? For example, when we tend to think that fields of particles, atoms are literally true, while they are just probably rather just theoretical entities that can be useful to describe some laws of nature. What is the scope or what are the limits of scientific knowledge?
Well, fortunately or unfortunately, there is no literal truth in science. And any given theory that seems to work very well now, seems to be explaining a lot of phenomena at some later time, may turn out to be incomplete. For example, Newtonian mechanics, Newtonian physics was a very well developed theory, but later it had to be replaced with Einstein general relativity. So it wasn't sufficient theory to explain all of the gravitational phenomena. Likewise, classical mechanics is a very good mathematical framework. It can explain a lot, but it had to be completed with quantum physics, and it was later replaced by quantum physics. it may very well be that both quantum mechanics and general relativity are just incomplete, and there is some kind of more fundamental theory that is to be discovered. Overall, we should understand that science doesn't really prove anything. It is just tries to model the universe around us, the world around us, better and better, and using the more advanced mathematical techniques, mathematical frameworks, mathematical tools that we have. So, for example, right now, people are interested in the mathematics of neural networks, and so one may ask, is there something that you can take with this mathematics and bring to scientific theories? Can it be used to model the world around us as a neural network?
And so what is the core idea of the neural network theory?
Well, as I said, the idea is to start with the mathematical framework of artificial neural networks, because they can be defined very well, and then see what can you model with it, like what kind of phenomena. So, for example, can you model the known physics? Can you describe quantum physics and general relativity using the mathematics of neural networks? Or maybe biology. Can you describe and model phenomena such as natural selection or other biological phenomena such as major transition of evolution, origin of life? Can you explain those things using the framework, the mathematical framework of neural networks? Now, if you can, then of course, next question would be, what else does it bring to the table? Can it resolve some paradoxes or perhaps inconsistencies or in the old theories? So in quantum mechanics, for example, we have a measurement problem that it is trying hard to explain and understand in context of the standard view of quantum mechanics. Now, in biology, emergence of life is something that is not well understood. Now, can, for example, those paradoxes or inconsistencies be studied using this new framework? And turns out it can, yeah. And we've done some of the calculations showing how quantum mechanics may emerge from the neural networks, and also how the origin of life can be explained as a phase transition. Now, of course, it is important that there is one new ingredient important to emphasize, that there is one new ingredient that comes with a neural network, something that wasn't present before, wasn't present in classical quantum physics. And it is the learning dynamics. So if you look at the mathematical framework of classical quantum or gravitational physics, there is no learning dynamics. That is something completely new. That is something that actually works against some of the well-established laws of physics, such as the second law of thermodynamics. A system that undergoes learning evolution, for that system, entropy can go down, and because of that, you can have life emerge, and more complex phenomena emerge from the learning dynamics. So this is something that we call the neural physics, and we are only now investigated the tip of the iceberg. We haven't looked at all of the possible aspects of the theory, but it is already proved to be very unique and interesting view on how the universe works.
And so can it be considered as the theory of everything?
Well, we don't know for sure yet, right? But we've certainly tried to model already many phenomena. I already mentioned physics and biology. We're also looking at some psychological and social phenomena. So far, things look rather promising, but of course, there's no guarantee that at some point we'll identify some phenomena or some inconsistency, internal inconsistency in the theory, and then we'll have to look for a deeper and more foundational theory than that. But so far, things look good.
Okay, and what are the fundamental elements of the theory?
Right. So usually any theory that is foundational, basic enough, right, has some elements, some ingredients, some smallest structures or objects from which the theory is constructed. So, for example, in particle physics, there would be fundamental particles. In string theory, that would be fundamental strings. Now, in the neural network theory, the smallest, most fundamental objects are neurons. We call them fundamental neurons to distinguish them from both artificial neurons on your computer or from biological neurons. However, it is true that they are just mathematical structures, the smallest mathematical structures. And the interesting feature about those fundamental structures that their dynamics is described by very, very simple rules. And yet, from that simple dynamics, you can see very complex behaviors. And that's what gives us hope that potentially you can use them to describe all phenomena. Again, something we haven't completed yet, but the more we look in different fields, the more we look at different phenomena, the more we see that there is something interesting that this theory provides. Now, of course, those fundamental neurons are the fundamental objects, and so there are certain questions that go beyond what this theory can answer. So we cannot ask questions: what happens on the scales smaller than those neurons, right? Presumably, those neurons is the smallest fundamental scale of the theory, perhaps the Planck scale.
So when we further mention neurons, we mean these fundamental tiny structures, right?
Well, that's right. So yeah, so they are the most fundamental structures. They are mathematical structures. Everything else you have is built out of them. But what is interesting that although the fundamental structures are neurons, as you start connecting them in networks of neurons, of fundamental neurons, you see the emergence of larger and larger structures that have essential features in their dynamics that resemble the dynamics of the fundamental neurons. So, for example, the biological neuron that is in our head, for example, is built of many fundamental neurons. It's built of many molecules, of many particles, and yet its dynamics, the learning aspects of the dynamics, resembles the features of the learning dynamics of the fundamental neural networks. And so that is an interesting thing, that certain features do appear on different scales. And so sometimes you would refer to neural network, not necessarily network that runs on the fundamental scales, but on the larger scales, like the scales of the organisms.
Okay, now when people hear neural network, when we hear it, we usually think of brain neural network or about artificial neural networks, the idea of which was based on brain neural network initially. Is this relevant, or what should we understand to distinguish this from the neural network of the world?
Right. So the artificial neural network or biological neural network or this fundamental neural network that I introduced, they have one feature that is essential for all of them, and it's the learning dynamics. So that is there, and it is the same. Now, also at the coarse grain description of those networks, you have nodes. Nodes are what we call neurons, and those nodes are connected by weights with varying strengths that determine how connected neurons are. And all that is present in all three examples of the neural networks. Now, in addition to that, you also have dynamics. So it's not just the state vector and weights connecting neurons, but also some kind of dynamics. And the interesting, again, aspect of the neural networks that there are two types of dynamics: the activation dynamics, where the state of neuron changes depending on the state of all other neurons and the strength of connections to them. And that is more or less similar to how evolution works, let's say, in classical physics or in quantum physics. But then there is something else. There's something new, that even the strength of connections between neurons can change and be adjusted due to the second type of dynamics that we call the learning dynamics.
Yes. So another thing that sometimes people think when they hear neural network, they also understand it as just network or web of life, or which also implies some kind of information exchange between the nodes. So what is the principal thing to understand to distinguish this from the neural network?
Right. So not every network I would call a neural network, in a sense that not every network would have learning. Now, information exchange is related to what I said as activation dynamics. It's you can have nodes, and those nodes exchange some kind of information, and we see it in different places. So, for example, the internet, the World Wide Web, we have computers as nodes, and the information flows through wires. And so you have that. You also have the cosmic web that apparently looks pretty similar to the biological network. But again, there is no evidence that there is a kind of learning dynamics there. So for now, all we see is that there is just, some kind of information flows between the nodes. And so exchange of information isn't enough for us to call something as a neural network. Now, if in addition to that, to the exchange of information, there is also learning dynamics that adjusts the strength of connections, then this becomes all of a sudden this becomes a much more complex system. And as I already mentioned, the second law of thermodynamics can be violated. The life may emerge, and all other very unique phenomena can occur if it is a neural network.
Mm-hmm. And yet another thing sometimes mentioning world as neural network goes along with the idea that we are living in a computer simulation. How can you comment on that?
Well, then you can take any theory and call it a simulation. If a theory, you take dynamical laws of a given theory, put it in the computer and say, well, look, I created a universe on the computer that is governed by the same laws. You can do that, although I don't think it brings anything new to the table. I don't think it probably is unnecessary complication. The theory as is does not need a computer on which it runs, right? So what it needs is the assumption of those fundamental neurons and the assumption of how they evolve, this type of dynamics activation and learning. And once you have that, everything else, or what those neurons are made of, or how they came into existence, all this is beyond the scope of the theory. The theory isn't able to describe it. Now, on the other hand, if at some point we will be able to test what those neurons are made of, then the theory would need to be completed, and you would have to look at, see, well, is it running on a computer or not, or what kind of new phenomena can you observe which go beyond the learning dynamics of neural networks.
Okay, so now how did the universe, what we see as a physical reality, how did it emerge?
Well, that's a difficult question, of course. Now, within the context of the theory, within the context of any theory, you have to answer the question, what is the Big Bang, right? How did the universe begin? Now, in the neural network theory, the answer is that there was a phase transition. There was a learning phase transition. There was a neural network before the phase transition and after. And the difference was that after the phase transition, a new, what you can call communication protocol was developed between neurons. Before the phase transition, all neurons could have been connected to each other. There were no constraints on the type of connections, and every single neuron would be able to receive information from all the other neurons. And presumably, for such neurons, their environment would look very chaotic and random, basically like a soup of randomly connected neurons. That was before, and after that, after the phase transition, the system, the neural network, this fundamental neural network of fundamental neurons, figured out that there is a more efficient way of communicating. This is what I call the new communication protocol. It makes sense to actually exchange data in effectively lower dimensional space. It's to organize themselves as lower dimensional structures. Now, why three is a good question. Why is it three-dimensional? Perhaps the answer here lies that one-dimensional structures were tried, one-dimensional organization of neurons was tried, maybe two-dimensional organization was tried, and that might have worked not too well, and so eventually a three-dimensional organization was tried, and that's what we call as the Big Bang phase transition. This is when all of a sudden the system figures out that it is much more useful from the point of view of learning to connect to its neighbors through this locality, three-dimensional locality, as opposed to being connected to simultaneously to all neurons.
And what could be the learning objective of that? What could be the loss function of this fundamental network?
Right. So right, exactly. So to decide it that one way of connecting is more beneficial than the other, you need to actually ask question with respect to what objective to. And in the learning theory, in the theory of learning, in the neural network theory, it is described by something that is known as a loss function. So what could have been the loss function? What could have been the learning objective for the neurons so that they figured out that they shouldn't be connected to all neurons, only locally, three-dimensionally. One possibility that they wanted to just learn their environment, each neuron. And if a neuron is connected to all neurons around, then presumably this signal is too random, and so not much sense can be made. So not much can be learned. And so learning the environment, trying to predict how the environment will change, is something that could have been the objective of learning objective on the most fundamental level. And because of this objection, the system figured out that it is advantageous to have a three-dimensional local connection as opposed to the infinite dimensional connection to all neurons.
And so the three-dimensional space is not real, is it?
Well, in this paradigm, of course not. This is just a useful way of exchanging information. And so there's no three-dimensional space on which those neurons live. If at a later time they discover that the four-dimensional is more beneficial, they'll do exactly that. Or maybe two-dimensional, then they will do that. But for now, yes, there is no, the space is not real, but that's a useful way of exchanging information. What's interesting is that once this three-dimensional structure was formed, it is unlikely that all of the neurons all of a sudden decided to join it. And so it should have been a gradual process, when some group of neurons discovers this new communication channel, discovers this low-dimensional emergent space, and then other neurons start joining in. Now, from physics point of view, or from the neurophysics point of view, it would look like a neurogenesis. Within this physical space, more and more neurons come into the existence, and therefore the space effectively grows. Now, from the view of the standard cosmology, that's just cosmic inflation, where you have this quasi-exponential growth of space. Now, to describe this, and it is also often a useful exercise when you're trying to understand some phenomena on small scales, try to look what it means on a larger scale. So we can think about an analogy from social networks. You have a group of people with like random connections between them, and then all of a sudden they discover some clever communication channel. Let's say they discover the internet, and then more and more people start joining in, and that's effectively what's been happening with the fundamental neurons. And so from the point of view of this neural network, it means just a fundamental neural network means more and more neurons figure out the usefulness of the three-dimensional communication, but from the view of the space, emergence space, it appears as the expansion of space.
So there are still some neurons that did not join this space and still remain somehow outside of it, right?
Well, that's right. Not as I said, not all of them would join the space right away, and there would still be some neurons outside of this physical space, three-dimensional physical space. Sometimes we refer to it as a hidden space, space that doesn't have immediate connections, obvious connections to our three-dimensional space. At least doesn't that hidden space, the neurons in that hidden space, they don't have a strong connection to our space. Because if they did, we would see it experimentally, right? However, they can still get connected, and so there can still be certain phenomena that that you can observe and calculate that are entirely due to this hidden space. So one example is a quantum phenomenon. It turns out for emergent quantumness, it is important to have a pool of hidden neurons. Now, this is a small-scale phenomena. There may be a large-scale phenomena. So things like dark matter may be attributed to the presence of those hidden neurons. Something we again investigating now, and something that we should look at now. But as I said, if it is a theory of everything, then presumably the presence of this hidden space, if it's real, has to appear on other scales. And for example, one might be interested to explore psychological phenomena that may be attributed to the presence of the hidden space.
Okay, let's say something about basic algorithms of information processing and exchange that neural networks use. What are those algorithms?
Right. So one we just mentioned, right? So the ability to communicate between neurons through the three-dimensional structures is an algorithm. This is kind of a decision that was made so that the learning of the environment would be more beneficial, right, to creating these local structures. But there are many others. And every new algorithms can be, the discovery of every new algorithm should be viewed in this theory as a phase transition. So one useful example that that can be explained in this context is the filtering of irrelevant information. Basically, when a neuron decided to join this three-dimensional space, what the neuron did is decided not to receive information from most of neurons and only receive information from what it considered to be neighboring neurons in a three-dimensional space. But of course, this phenomena, this algorithm, once it was discovered, it can be applied on different scales and for different systems, for different subsystems. And presumably for larger systems like particles, cells, observers, there is still this ability to use this filtering algorithm. The particle may not be able to do that, to decide what to receive or not, but cells certainly have filters. Well, actually, particles have that too. And so cells have filters. They decide what kind of information they want to receive and which they don't want to receive. Same like multicellular observers, right? They also have this ability to decide whether to receive certain information or not, to filter it or not. So that's one useful algorithm. Another one is compression of information. So, for example, you receive information from the environment, and you want to make a decision of what to do with this information, and you want to keep track of as much information as possible. But of course, to do it efficiently, you want to look for some correlations, some features in the incoming data. And once you figure out the correlations and features, you can compress information received and then store it, presumably locally first, so that you can later use this information to achieve your goal of understanding environment or modeling the environment. Now, there may be, of course, more advanced algorithms where you receive information, you first compress it, and then you decided to store it someplace other than inside of this subsystem or agent. You may, for example, write it in a book or on a disk drives, right? So that would be a way for you to record information that you received. You can also do things like outsourcing computations, right? So I can use my computer to add, subtract numbers rather than doing it in my head. So all of those are algorithms that are available for observers on very different scales.
And these filters, are they dynamical? So that subsystem can adjust the filters and change some communication channels that it uses.
Right. So subsystems, subnetwork, or what we can call agents, can have this, again, add-on to the algorithm, filter algorithm, and say, well, not only I'm going to be filtering information, I'm going to be changing the filter dynamically as I go. So, for example, we as humans have this ability to change filters. We can concentrate on one type of information that is incoming and filter the other. We can read the book and ignore the sound, or other things like that. So this is something that is available for us for sufficiently complex subsystems or agents, which may not necessarily be available for long or smaller systems. But it is, again, some additional algorithms that needs to be discovered for sufficiently complex systems.
And this using the resources of another subsystem that you mentioned, how does it work? You mentioned that the system may happen to use some other subsystem for compression and storage of information, and also to perform computations.
Well, that's right. Yeah. So I think the way to picture it is that there is what you call subsystem or a subnetwork or maybe agent. And then there is this physical environment, everything outside of this subsystem in the three-dimensional physical world. That's a second part. And the third part is this hidden environment, right? So, all those three parts that you consider can use any of the algorithms I described in very different combinations. So you may compress information that comes to the agent or to the subsystems, and then decide to store it in a local physical space right outside. Or you can presumably, if there isn't this ability, you may be able to even try to store it uploaded to this hidden space, and then for the later use whenever you need it. You can do the same with computations or information processing. You can either locally process information, and an agent, a subsystem, can either locally process information, or it can use the external resources, whether in the physical or in the hidden space. So all these algorithms that are being used, they're universal in the sense that they can be used for also at any level. So right now we are describing just the level of humans because this is the level that is most familiar to us. But we can ask same question on other levels, like the level of cells or particles. What do this type of filtering and compression algorithms are on those other levels, as well as on the higher levels, on the levels of the society as well.
Can you give some more examples of
Sure.
that?
Sure. So let's take the compression algorithm. So as I said, it may not be available on all scales. So the compression, for example, doesn't seem to play a role in how atoms or molecules are fundamental particles interact, right? But the compression is definitely used at the level of humans. Now, whether, because that's what we do when we look around, we look for patterns, right? So if we see patterns, that's how we better memorize a given state, and then we can better understand how that environment would work. Now, whether this is an algorithm that is being used at the level of society, we don't know yet, but it's definitely in this for sufficiently complex systems, it is definitely in use. Now, another example of using the hidden space, right? So I said, there is this hidden space, then on which level would it be useful? Would it be useful on all levels or just maybe on the on some particular level? So we already mentioned that for the emergence of quantum mechanics, which is a phenomenon that appears on the smallest scale, the presence of the hidden neurons of the hidden space is essential. Now, and so we do observe that on the smaller scales. Whether it is also important on larger systems, that is not clear, at least not clear yet. So maybe it is, maybe it isn't. And again, but all those things should, in principle, be experimentally verifiable. But perhaps if you are trying to study the interactions of the hidden space with a human, that belongs to the psychological level, and on that level, we need to do some work even before we start testing the ideas of the hidden space. First, we have to actually develop experimental methods within the context of the theory, as well as the theoretical methods. And that appears to be a challenging task that we are working on.
Okay, great. Now the next important concept is multi-level learning. So what is multi-level learning? What are the different levels? Let's talk about that.
Right. So I already kept saying levels, but it is not only something that we observe around us, which we do. So if you look around, there are structures on the small scales like particles, electrons, protons, and then there are atoms, molecules. On somewhat larger scale, if you go to even larger scales, there are cells, organisms. Then we have on cosmological scales, we have galaxies. So we see this appearance of scales from very small to very large. But the interesting perspective that this hierarchy of scales actually a emergent phenomena that had been observed in machine learning systems, in systems that undergo learning dynamics. And so this hierarchy of scales, as present in nature, we see it, and also present in the learning system that we have experimented with. This is what we call multi-level learning. So basically, the claim is that learning happens on all scales, and that's what multi comes from. And the only difference that on some levels you can have some algorithms present and others may not be present, but the essential learning dynamics seems to be present on all of those scales. And so this is then how do you distinguish between different levels? In this multi-level learning paradigm, the distinction between them comes from the scales, temporal scales, on which certain degrees of freedom on those levels, relevant degrees of freedom in those levels change. So for the smallest systems, for the microscopic levels, for the smallest level, you have lowest level, things change very rapidly. And for the higher levels, things change relatively slowly. And so another interesting outcome of this multi-level learning paradigm is that for the high-level system to actually be able to take into account the behavior of a lower-level system, it has to do something that is called renormalizability. You have to renormalize or coarse grain over the high frequencies or a smaller time scale, all those fast-changing degrees of freedom. And you can only do that in certain theories that are called renormalizable. So kind of a prediction of that comes out of this theory. If universe is observable, if there are observers that can learn the environment, that must be renormalizable. So presumably one possibility is that this hidden space actually is not normalizable, and so there are no local observers, and something chaotic happens there, which may or may not be true. We don't know that, but for the very least, our physical space is renormalizable, and we have this hierarchy of different levels where the only real distinction between them is that some levels had discovered some new clever algorithms, others haven't. And so in this view, even biological evolution itself is an outcome of the learning dynamics, and so appearance of this new biological level where the things take place.
So what we have are agents on different levels, and those agents can have conflicting objectives, and if something gets broken, we get cells that on organisms whose goals are different from the goal of the whole organism, and this kind of conflicts happens everywhere. And so how does that get resolved?
Well, it doesn't, right? So this is what we call frustration or conflict between different levels. What is beneficial for organism may not be beneficial to its cells, and so there is a conflict between higher level with a lower level. But also something that's beneficial for organism may not be beneficial to the group of organisms. So there's always this conflict, and you cannot really find an optimum solution. You can never find an optimal solution in this non-trivial machine learning systems. So that sounds really bad. Sounds like, you can never find a good solution, but you can find an okay solution. And this okay solution, the learning dynamics that gives you to finding better and better solution, which may not be optimal, is driving actually all of the phase transition that I mentioned earlier. It is because the system, if the system gets stuck in the local minima, it's tried everything it could with the existing algorithm. The only thing it can do is to actually improve the algorithm. So make filters dynamical, or introduce compression, or introduce the use of external resources. And so this frustration of never acquiring the perfect solution that would satisfy everyone is what drives this evolution of complexity. And important to emphasize that this has to occur on all scales. And we should not stop when you're talking about multi-level learning on only biological scales or physics scales. We can try to apply the same logic to psychology, to economics, politics, and beyond. But even at the level of the physics and biology, the various phase transition took place. So one of them, as we know, is origin of life, but there are many others. Formation of multicellular organisms from single cellular organism is another example. And so this is a never stopping process of creating a more and more complex system, is an outcome of this inability to find the optimal solution, and always trying to find a better and better okay solution.
Okay, and a bit more on how those levels are defined. For example, what we can say about the interaction between a human level or human society level with the level of the biosphere. On one hand, biosphere sounds like some biological, and on the other hand, it looks for me like it involves somehow psychological and social levels.
Right. Yeah, I think biosphere is the highest level, at least here on Earth. So it includes biology of individual organism. It involves the groups of organisms. It involves the level of human level of societies, and so all of those levels are kind of included and remain lower than the level of biosphere. Now, of course, and then also, like, as you mentioned, like politics or economics, all those levels come into play when you discuss how the biosphere evolves. Now, of course, the difficulty with every new level, which includes a biosphere level, is that it becomes increasingly complicated to model things analytically. There is a lot more level under them and a lot more parameters and a lot more complexity that goes in their dynamics. And also it's even hard to model numerically. I'm not saying impossible, but at least the tools that we have, both analytic and numerical, do not allow us to do this. But then there is the one approach that physicists often use, so-called phenomenological approach. So basically, yes, you may not be able to explain the appearance of all those new levels or how they evolve, but you can try to concentrate on certain macroscopic parameters and try to model how those macroscopic parameters evolve, as opposed to microscopic parameters. So you would be looking at the thermodynamic-like quantities, temperature, entropy. By temperature, I don't necessarily mean the physical temperature, but the temperature, on whatever level, learning temperature, on whatever level you're trying to do the modeling, and the same for the entropy. So you would be using them, temperature of entropy, as your variables that you try to explain how they would evolve, as opposed to state vector of fundamental neurons or the weight matrix. And then in principle, you should be able to measure the system or two systems, maybe they have different temperature, different entropies, and then see how things would evolve and make predictions how the system would evolve and make statements whether the system is about to undergo phase transition. For example, it's unstable, or is it relatively stable and the good local minima had been reached.
And at the same time, this fundamental level is still present in every network, isn't it? So a human body is the network of cells, bacteria, and we can talk about, we can consider it as the network of those. And also at the same time, it is still a network of these fundamental neurons, right?
Well, that's right. So absolutely. Everything is built out of fundamental neurons. Sometimes the language where we use fundamental neurons is not useful. And then you have to actually go and define those more macroscopic quantities. So I mentioned temperature, I mentioned entropy, there are many more, chemical potential, blah, 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 and all of those things that become more useful at the higher levels. So yes, the answer is the fundamental neurons are always there, but the language is not necessarily useful on the other scales. And then you have to readjust what are your relevant parameters that you're keeping track at any given level.
And what happens with the death of an organism? What happens on a higher level network?
Well, death, as you might have guessed, is just another algorithm. It's another phenomena, but also in terms of the neural network theory, is just another algorithm. Now, it doesn't look at it as beneficial for the organism that died, right? So its loss function went up before the death. It was able to predict very well, relatively well, its environment, but after the death, it cannot do that. So loss function definitely went up. But it is beneficial for the higher level. It may be beneficial for the higher level, for the group of organisms. Now the organism is not using the resources, and so presumably these resources can be redistributed between different other organisms, and that would benefit this level of the group of organisms. So it is again kind of a conflict, but the death takes place it is resolved. It didn't. It's not an optimal resolution. Nevertheless, it is a resolution. Now, also, since we're talking about death, there are also two more, or I guess one more relevant phenomena: sickness. Right. You can also add aging to this. So when a person becomes sick, or why does it age? So you may you can basically take any phenomena you like and try to see what it means in terms of the neural network theory. But for the aging or sickness, it seems to be overfitting. So this is a phenomena that is observed in a machine learning system. It's very well known. Basically, what it tells you is that the system or agent, as we now call them, may be very good in learning their current environment, and their loss function may be very, very small. But then environment changes, and all of a sudden the observer, the agent, is not able to predict its environment, and it eventually dies. So it cannot quickly adapt to the changing environment. And so this inability to adapt can eventually lead to death, unless it learns how to overcome this problem. Now, in fact, the inability to adjust to a changing environment might have been the cause why dinosaurs died, right? And then you may say that dinosaurs died because of overfeeding. They were well prepared for the current environment, and then the environment changed. They were not able to adjust.
And what happens with the information that an organism have learned during its lifetime? What happens with that information when it dies? Is it gone?
Well, not necessarily. First of all, it can definitely exist in a physical space, right? So you learn something and you can pass it on to your children, to your students. You write it in books, internet, all those usual phenomena of copying your information and storing it in some more stable places still exists there. But then there is also this possibility, again, that wasn't explored further, needs to be explored further, is that some of that information may be actually uploaded to the hidden space, right? We discussed it already. This may be a useful learning phenomena, learning algorithms. And if it is, then maybe even if there's no imprint of organs that died in the physical space, nothing left, there may still be something in the hidden space. Again, very speculative thought, but there is nothing in this theory that would tell you that this isn't the case.
Okay, agents. How do they emerge in this global neural network?
Right. So agents are basically are clusters of highly connected neural networks. Within the network, within this cluster, neurons have strong connections with each other. Now, the connections to the outside networks, subnetworks, is smaller. So the appearance of clusters seems to be again something that is an algorithm that is beneficial for learning, because smaller subnetworks may not be able to receive lots of information, process it, and so this type of collaboration and formation of clusters is expected. But of course, once you form your first cluster, I don't know, maybe elementary particles of such clusters, you see that the formation of clusters this also becomes beneficial. Again, this idea that certain phenomena present on all levels, and so then everything becomes kind of a cluster. You have elementary particles that are clusters of small clusters of the neural net fundamental neurons. Then you have molecules that are larger clusters that again are heavily connected within themselves, but have a weaker connection to the outside. And then you have clusters of cells, then multicellular organisms, society, etc.
So how is the border of cluster defined?
Well, by the strength of connection, right? So within the cluster, the connections are very strong. And so if the connections are strong, you kind of have a boundary. It's not a sharp boundary, but nevertheless useful boundary for doing calculations. And then you define this, and you say all the connections within the cluster are strong, much stronger than the connection to the outside, to the external space or to the environment.
And are those weaker connections used for the interactions of the agent with the environment?
Right, exactly. Right. So you don't want to cut out all connections. You still want to have some interaction with the environment, because after all, as we discussed in the beginning, the loss function might be to learn the environment, right? So this would be the learning objective. And then there are those two environments, right? There is a physical world and a physical environment, and then there is a hidden world and a hidden environment. And so basically, you can have connections to all of them, and then you can also impose filters and change your bandwidth of connections. And for example, you can try, one agent can decide to connect to another agent within its own environment and establish those connections. And moreover, even within your within that cluster, within an agent, not all neurons play the same role in these communications, right? So there'll be some neurons that are especially designed for communicating, like through sound or through light, and other neurons are more for information processing and building the model of the universe inside. So there are different tasks, responsibility of different neurons within each cluster. It's not like everybody is doing the same job. And then once those communications are established, whether to the physical world or maybe even to the hidden world, then you can use all of the usual techniques we discussed before. Maybe you can use a compression algorithm for the protocols. So you can have two agents that would be communicating with each other. Maybe they use sound as a communication channel, but then they want to also have some kind of compression, and then they may introduce different communication protocols, languages, alphabets that would make this communication have more error-proof, let's say. But then you can also have a more abstract communications that maybe we don't have any evidence suggesting that this is the case, but presumably you can have weak connections that go not through the physical space between two agents, not through the physical space, but direct connections. Maybe telepathy is an example of that. Again, something that should be checked, verified experimentally. Maybe yes, maybe no. Or maybe you can have some connections to the hidden space, like divinations, or I don't know, some kind of other psychological phenomenon that we should be investigating. And so the ability of us to actually measure those connections and see what they're used for is essential for actually testing the whole theory at the level of, at the psychological level, for the very least.
What is consciousness?
Oh, well, that's a difficult question, right? And I think in this neural network theory, there is one interesting possibility. Again, not saying this is the one, but interesting possibility that that can be very well defined mathematically. You can calculate and find a number that would tell you how conscious a given system is. And that number is what is called the efficiency of learning. Now, more precisely, it is a decay rate of the loss function when the system is learning. So basically, the higher the decay rate, the faster the system is capable of learning. So it's more efficient in learning, the higher consciousness of the system is. Now, so for example, and of course, to be an efficient learner, as we already discussed, you need to have clever learning algorithm discovered at your disposal. So, for example, you can have molecules, right, that they're relatively poor learners. They're not very efficient learners. They don't, for example, have dynamical filters. So a molecule that cannot decide whether it's gonna interact or not interact with photons or with electrons. It doesn't. And so they're relatively poor learners. And so in this with respect to this theory, they would have a lower level of consciousness. Now, cells are better learners. They do have filters. They can filter out irrelevant information and only receive the relevant information. And so they are somewhat better learners. They are somewhat more conscious. And then you have organisms, right? Larger organisms, multicellular organisms that are even better learners. They have not only ability to receive filter irrelevant information, they maybe even have the ability to model themselves. And so they're not just modeling the environment, they're modeling themselves in the environment. And that seems to be an even more advanced learning algorithm, meaning that they have a higher efficiency of learning and higher consciousness. Now, of course, as I said, efficiency of learning has a well-defined mathematical expression for a decay rate of the loss function. So presumably, in principle, it should be possible to build something like a consciousness meter that you can stick it into any subsystem, into any agent, and figure out how conscious this system is. And maybe if it's a highly conscious system, then the meter would show high value, high level of consciousness. If it's more like physical system and it doesn't have what we call life in there, then it will score low as a consciousness system. But nevertheless, in both cases, it is not a discrete quantity, like something is conscious or not conscious. There is a continuum of values. We can just say something is more conscious and something is less conscious.
Okay, and trying to correlate this understanding with some other opinions, versions, there is no unified understanding of the term consciousness within the conventional scientific field still, but in some versions still the consciousness is considered to be somehow emergent from a complex biological system, in particular related to human brain. How would you comment on that?
Well,
on the consciousness relation to the human brain.
Yeah, in this theory, everything is conscious, right? So it's only the level of consciousness that is different. Now, presumably human is a lot more conscious because the system had undergone many phase transition and it has a high level of consciousness. Now, maybe there are even higher levels of consciousness than human levels. For example, there may be a level of, maybe a consciousness at the level of society. And that we can, presumably measure if we had this working consciousness meter. But the short answer, yes. So everything is conscious. It's only the level of consciousness that is different for different systems. And without this working consciousness meter, it is hard to be sure which system has a higher or lower level of consciousness.
In Vedic philosophy, consciousness is seen as a fundamental property. How can we relate this with the neural network theory?
Right. So in the neural network theory, the entire universe is learning. And so in a sense, entire universe is conscious. Every subsystem of this network is learning. And so every subsystem of the universe is also conscious. Now, however, the consciousness isn't the fundamental aspect of the theory. it is a property. It is a property that you can measure for a given subsystem. What is the fundamental aspect is learning, is the learning dynamics. And so it's not exactly the same in a Vedic philosophy, yet it is pretty close in a sense that in both cases, consciousness seems to be present throughout the universe.
And what is self? How does it emerge?
Right. Again, we kind of a little bit mentioned that, but you have an agent, and it is task is to model the environment, to predict the environment, and then at some point the agent decides that, well, let's try to model not just the environment, but model the environment with me present in there. So model self, to have a model of self in the environment. Now, the agent can try it and see whether it is beneficial. Now, and very often it is. If you have a sufficiently large system which has enough resources to model that self, that's what exactly the agent should do. So this is, again, an example of a phase transition that should take place. The agent should figure out the necessity or advantages of modeling self. Now, presumably, this is what happens even with babies as they grow old. In the beginning, they just open their eyes. For them, there is universe. There is no notion of self. But then eventually, they discover different parts of their body, and they understand that they are part of this universe, and it is beneficial for them to model self. Presumably the same thing happened throughout evolution. So there was some kind of a self phase transition. Before, there were some primitive organisms. They don't have this ability to model self. For example, cells may not have the ability to form cells. However, they don't have enough resources for that, right? But then multicellular organisms do have those resources. And the self phase transition would have taken place by cells figuring out that individually they cannot do that. So let's combine together, form an organism. And then as an organism, we would have a high level of consciousness that has this model of self as an algorithm, but also because of that high level of consciousness. And because of that, the learning efficiency is higher, and therefore the model of environment is a lot more accurate.
So then can we suppose that at some point, yet another algorithm other than self may appear?
Well, of course, right? So the learning never stops, and so the systems are figuring out more and more advanced algorithms. At some point, it may be that our agents discover that modeling themselves as a separate self is not beneficial, and so they can merge into something that form a joint unity, and that joint unity would have a model of self, but not individual parts.
And what can we say about the universe? Is it conscious, or how conscious it is?
Right. So as it looks that this efficient self-learning and the high and higher level of consciousness is something that constantly grows in the universe. And so we already have a lot of self-aware parts in it that have those models of selves. However, the society for now is too disjoint. There is presumably it doesn't add much to, at least our society here on Earth doesn't add much to the overall efficient self-learning. We're still pretty good disjoint learners. We still learn things pretty well by ourselves, but not as one unity. So now, but of course, at some point, this phase transition may take place, and then there's a higher level of super intelligent observer may be formed. In fact, this may actually we may be getting close to this self transition now, because now we haven't made this phase transition yet, so we're still disjoint. But this may explain the so-called Fermi paradox, discrepancy between the lack of evidence of aliens and the high likelihood of their existence. So basically, the answer would be that if the aliens were advanced enough, they would have already joined in this super intelligent observer, and so we wouldn't see them as aliens. We wouldn't perceive them as aliens. But again, just to repeat, important point that currently the level of consciousness in society is relatively low. It doesn't add much to the consciousness of individual observers. We are too disjoint. We are not kind of we do not have like one common goal that we are trying to achieve. Too much of the disconnect in this, at least at the level of society. But presumably, once this phase transition takes place, things will change.
And what about the hidden space? Can it be that some higher level of consciousness already exists in this hidden space?
Right. So again, one possibility that we are not there yet. Okay, we haven't created a higher level consciousness. Second possibility, maybe some aliens already created it and so exist in the physical space. And the third possibility is actually already exists, and it is not part of the physical space, but the part of the hidden space. Now, if that's the case, it's a very interesting possibility. If that's the case, then we may be able to use it, right, somehow. Now, for most of us, have no connection or connections to this hidden space are very weak. But if there's such a consciousness, super intelligent consciousness exists in this hidden space, presumably we should be able to learn how to adjust our filters so that we can use it to perform useful information processing. That's certainly a very interesting possibility. Yeah.
And can the existence of the hidden space or hidden consciousness be somehow verified experimentally at all? And is it self-aware, meaning does it have a model of self? Could it have a model of self?
Well, the first question is I think easier. The existence of the hidden space we can verify, and that appears to be at the level of doing the quantum experiments. So as I already mentioned, theoretically, we've conducted calculations showing that there has to be some hidden space of hidden neurons, and with them you can see the emergence of quantumness in our physical space. So in principle, we can verify this experimentally, this hypothesis, and confirm the existence of the hidden space at the level, at the macroscopic level. Now, whether this hidden space is actually conscious or it has high level of consciousness, self-aware, now that's much more difficult task, because for that, first of all, we need the consciousness meter, and then presumably consciousness only exists at the higher levels. So we should be trying to see, not only test that there is this hidden space, but actually be able to explore a large portion of this hidden space. So there are like kind of two relevant phenomena. One, hidden space, and we see it in the smaller scales, and the other is consciousness, high level of consciousness, which we seem to see only for sufficiently larger systems. And so for now, I'm not saying it's impossible, but for now it seems to be a challenging test of testing whether the hidden space has consciousness, high level of consciousness.
Okay, great. And the last question for today's topic for today is in which fields this neural network framework can be useful, how it can help in research across the various fields?
Sure. As a theory of everything, if it is a theory of everything, in principle, we should model literally everything. Now, of course, the level of rigor or the power of making prediction may vary between different levels. And for some levels, this new theory can give you lots of good insights. For others, you will have to work carefully in designing the right experiments in order for it to be verified. So it's a challenging task. But the one important point to make here is that since in this theory we have this emergence of multi-level learning, because of that, you may be able to do a little trick. You may be able to perform certain experiments on one level and then use the results of these experiments and apply them to some other level. So, for example, you can do some experiments on the level of physics and biology, where things seem to be a lot more under control, acquire understanding of how physical or biological system behave, and then seeing, okay, well, if this phenomenon is present on that scale, maybe it should also be present on other levels like society or level of society, and then apply it there. So you do experiments on one level and then apply it on the other level. And vice versa. Maybe there are some experiments that are easily conducted or observation at the higher levels, and then you may, after appropriate adjustments of constant and etc., after what we call renormalizing the constants, but then you can apply it to some other level. So if that's possible, that is certainly something that needs to be done. Also, on a more practical level, if you learn certain algorithms that prove to be useful for learning, then your immediate question should be, why not use it in machine learning, right? So it's more practical level. You've discovered, let's say, natural selection. Well, let's apply it to machine learning. You discovered the program death algorithm. Let's apply it for the machine learning or dynamical filters. So that would be a more practical level. Now, if we really want to explore all possibilities, then of course we should also mention philosophy or religion and the ideas that already exist in those fields, and see how those ideas can be adapted for modeling some phenomena or for understanding how neural networks, learning systems work, and also understanding the role of completely, for now, what seems to be unscientific and abstract things like art. But yet again, this would be something that in the context of this theory would have to emerge. And if we want to study it, we should try to understand it both experimentally and model it theoretically, and then see how this can be used to understanding phenomena on higher levels, so like society levels, where art may give some useful insight to the dynamics. So all those questions are very important, and certainly we wouldn't have enough time to discuss all the possibilities. We are working on all of this, but that is something that we should definitely carefully analyze and see what all those fields have to give us in terms of experiments and observation, and as well in terms of theoretical modeling.
Great. I think that's all for today. Thank you very much, Vitaly.
Thank you, Katya. It was great.
Thanks everyone for watching. And in the description, there will be the links to our groups, and you can join our group meetings. And if you have some questions, comments, objections, ideas, you can come to discuss it. Also, you can write it in our chats, or you can write it in the comments to this video as well. So that's it for today. Thank you. Bye-bye.
Thank you. Bye-bye. Bye.